There's a jet engine sitting in a museum in New York City. Not a model of one, not a photograph. An actual piece of an actual engine mounted on a wall in the Museum of Modern Art, in the same building where people go to look at Van Gogh and Picasso. It's a single fan blade, 4 feet long, onyx black, curved like something that grew rather than something that was built. And it came off the most powerful jet engine ever certified to carry passengers. That blade is from the GE90 115B. And the story of how that piece of carbon fiber ended up in an art museum is really the story of how a company almost went broke trying to build it, how it spent nearly $2 billion on an engine that airlines didn't want, and how that same engine, the failure, the embarrassment, the money pit, ended up defining what a modern airliner even is. So let's start at the beginning, not with the GE90, with something older. Because to understand why the GE90 was such an enormous, terrifying gamble, you have to understand what happened to the last company that tried to leapfrog the entire industry with one engine. And that company nearly ceased to exist. Rolls-Royce, 1971. Here's the setup. In the mid-1960s, Lockheed was designing a new wide-body airliner, the L1011 TriStar. 3 engines, big cabin, meant to go head-to-head with the McDonnell Douglas DC-10. And Lockheed needed a power plant. Rolls-Royce showed up with something extraordinary on paper, the RB211. Now, what made the RB211 special wasn't just power. It was the architecture. The RB211 was the first production 3-spool engine. 3 concentric shafts, each spinning independently, each optimized for a different pressure stage inside the engine. Nobody had put that into production before. It promised better efficiency, lower noise, better performance across the whole throttle range. And there was one more thing. Rolls-Royce wanted to make the fan blades out of carbon fiber composite in the late 1960s. Think about that for a second. Composites in a fan blade on an engine that would fly paying passengers at a time when the material was barely understood. Lockheed loved it. Lockheed felt that the new engine enabled the L1011 to offer a distinct advantage over the otherwise similar DC-10 product. So they signed. And here's where it gets ugly. The contract was fixed price. Rolls-Royce agreed to deliver engines at a set cost, no matter what it took to build them. That's an enormous bet, and it only pays off if development goes according to plan. Development did not go according to plan. During development testing, the carbon fiber fan blades failed durability requirements. Bird strike tests exposed structural weaknesses. Rolls-Royce was forced to abandon the composite blades and replace them with heavier titanium alternatives. Heavier blades meant a heavier engine. A heavier engine meant worse performance. Worse performance meant redesign. Redesign meant delay. Delay meant money. Bleeding money. By autumn 1970, the launch cost for the initial batch of 53 engines had risen to £135 million, significantly higher than prior estimates of around £75 million. The numbers stopped making sense. And then, on a February day in 1971, one of the most respected engineering companies on the planet simply stopped. By January 1971, Rolls-Royce had become insolvent, and on the 4th of February 1971 was placed into receivership, seriously jeopardizing the L1011 TriStar program. That's it. Rolls-Royce, the company that built the Merlin engine that powered the Spitfire, the company whose name is a synonym for quality in the English language, receivership, because of one jet engine. And the fallout was international. Lockheed's entire aircraft program was designed around a single engine supplier. Unlike the DC-10, which could be fitted with multiple engine options, the TriStar was locked into a single supplier. No Rolls-Royce, no TriStar. Full stop. So the British government stepped in. Because of its strategic importance, the company was nationalized by the Conservative government of Edward Heath, allowing development of the RB211 to be completed. As Lockheed was itself in a vulnerable position, the British government required that the US government guarantee the bank loans that Lockheed needed to complete the L1011 project. Read that again. The British government nationalized Rolls-Royce and then turned to Washington and said, "If we're saving this engine, you're saving the aircraft it goes on. Otherwise, there's no customer and we're throwing money into a hole." Despite some opposition, the US government provided these guarantees. In May 1971, a new company called Rolls-Royce 1971 Limited acquired the assets of Rolls-Royce from the receiver, and shortly afterwards signed a new contract with Lockheed. This revised agreement canceled penalties for late delivery and increased the price of each engine by £110,000. And here's the part I love. To fix the engine, they went and got a retired man. Kenneth Keith, the new chairman who had been appointed to rescue the company, persuaded Stanley Hooker to come out of retirement and return to Rolls. As technical director, he led a team of other retirees to fix the remaining problems on the RB211-22. A crew of pensioners pulled back into the building to save the company that had let them go. The engine was finally certified on the 14th of April 1972, about a year later than originally planned, and the first TriStar entered service with Eastern Airlines on the 26th of April 1972. Hooker was knighted for his role in 1974. Hooker had a line about the whole experience that says everything about the scale of it. We added a 0 to his stature. He used to think £5 million a lot of money, but after a few weeks on the RB211, he came to understand that £50 million is peanuts. But the damage was done. The delay with the RB211 engine allowed the DC-10 to enter the commercial market first, which allowed the aircraft to capture additional airline orders. Lockheed only delivered 250 L1011 TriStars to airlines. Lockheed eventually walked away from the commercial airliner business entirely. So that's the ghost. That's what was hanging over the industry when, 2 decades later, General Electric decided to build the biggest jet engine the world had ever seen. Now, hold that thought about the composite blade that Rolls-Royce couldn't make work. We're coming back to it. Fast forward, 1990. Boeing is launching the 777. The 777 was a genuinely radical proposition. A twin-engine wide-body meant to fly transoceanic routes over the Pacific, with only 2 engines. If you grew up thinking that's normal, it's because the 777 made it normal. At the time, the idea of crossing an ocean with 2 engines instead of 4 made a lot of people nervous. And a twinjet that big needs monstrous engines. 3 manufacturers lined up. Pratt & Whitney offered the PW4000, Rolls-Royce offered the Trent 800, and General Electric offered the GE90. Here's the crucial difference, and it's the whole story in one sentence. As one of the 3 available engines for the all-new Boeing 777 large twinjet airliner, the GE90 was an all-new $2 billion design in contrast to the offerings from Pratt & Whitney and Rolls-Royce, which were modifications of existing engines. Pratt and Rolls were stretching engines they already had. GE was starting from a blank sheet. Let's talk about the competition first, because they were not weak. The Pratt & Whitney PW4000 had one enormous advantage. It wasn't new. One of Pratt & Whitney's key advantages in the PW4000 is its significant parts commonality with other PW4000 Chord engines powering aircraft such as the Boeing 767, 747, 400, as well as the McDonnell Douglas MD-11 and the Airbus A330. If you were an airline already running PW4000S on your 767S, you already had the spare parts, the trained mechanics, the tooling. That's not glamorous. That's just money in your pocket every single day. For many operators, this commonality was a deciding factor whose resulting savings in service and parts inventory costs more than offset the lower thrust growth potential and higher specific fuel consumption from this older core design. The 777 specific version, the PW4000-112, named for its 112 and 2.8 M fan, was no joke either. Development began in October 1990, achieved 100,000 lbf 440 kN in May 1993, and was approved for 180 minutes ETOPS at service entry in June 1995. And it won the launch. The 777 launch engine, it entered service on the 7th of June 1995 with United Airlines. United, the biggest, most influential customer in the room, picked Pratt. Rolls-Royce, meanwhile, brought the Trent 800, part of the family that had literally grown out of the RB211's ashes. The RB.211 was renamed in 1989 to become the basis of the Rolls-Royce Trent family of engines when the RB211 524L was renamed to the Trent. That's a full-circle moment if you think about it. The engine that bankrupted the company became the foundation of its entire modern business. So there's GE, blank sheet, $2 billion, and an idea nobody had successfully executed. And it's worth pausing on something here, because GE built the GE90 inches is a convenient shorthand that isn't quite true. The engine was an international program from day one. GE Aviation teamed with Snecma France, 24%, IHI, Japan, and Avio Italy for the program. Snecma of France took nearly a quarter of it, IHI in Japan, Avio in Italy. Launched with European revenue-sharing participants, Snecma of France and Fiat Avio of Italy, and Ishikawajima Harima Heavy Industries IHI of Japan, the GE90 family was the only new centerline engine developed for the Boeing 777. Revenue-sharing participants. That's the model. You put in money and engineering, you take out a slice of every engine sold, forever. It spreads the risk of a $2 billion bet across 3 continents. And given how the first 8 years went, those partners had some very uncomfortable board meetings. Now, the technology. They wanted composite fan blades. Before we get to why that mattered, let's make sure we're on the same page about what a modern turbofan actually is. Because most people picture a jet engine as a thing that burns fuel and shoots fire out the back, and that is almost entirely wrong. Here's the honest version. It's a type of engine known as a high-bypass turbofan. Used in most modern airliners, the turbofan is a propulsion system in which some of the air taken in is compressed, burned in a combustor, and expelled to generate power for driving the fan and compressor. A greater amount of the air bypasses the combustion process. Read that last line again. Most of the air never gets burned. In the GE90, the relatively cool bypass air is pushed rearward by a huge fan to mix with the hot exhaust gas. The result is a very large gain in overall thrust with minimal fuel expenditure. So the core, all that machinery, the compressor, the combustor, the turbines, the fire, exists primarily to spin the fan at the front. The fan does the work. The fan makes the thrust. Propulsion engineers use the term bypass ratio to indicate how much of the ingested air bypasses the combustion chamber. Generally speaking, the higher the ratio, the more efficient the engine. Which means, the bigger the fan, the better. Always. Bigger fan, more air, more thrust for less fuel, less noise. Everything about the last 40 years of jet engine design is a story of engineers trying to make the fan as enormous as they possibly can and then fighting the consequences. And the consequence of an enormous fan is weight, which brings us back to composite blades. Now here's what's beautiful about this. Remember Rolls-Royce, 20-something years earlier, trying to make carbon fiber blades and getting destroyed by bird strike tests? GE looked at that history and said, yeah, we're doing it anyway. But they weren't starting cold. NASA gave GE a grant in February 1984 to continue its research, eventually building the experimental GE36. One of the major innovations for the engine was its carbon fiber composite fan blades, which were both lighter and stronger than traditional materials. The GE36 is one of the great what-if machines in aviation. It was an unducted fan, an open rotor. It had used carbon fiber composite blades in an unusual hybrid design that combined features from turbofan and turboprop engines. Imagine a jet engine with the fan blades exposed to the open air, no cowling around them, spinning like a propeller from the future. And the fuel numbers were extraordinary. Although the engine demonstrated fuel savings of more than 30% compared with similarly sized conventional jet engines, it did not catch on. 30%. In an industry where a 2% improvement gets a press release. So why did it die? A few reasons, and they're all commercial rather than technical. However, the UDF was less reliable than the turbofans of the era. Lower fuel costs made the cost of the engine's development less attractive, and the company was worried the GE36 would cannibalize sales of the highly successful CFM56 engine it had co-developed with Snecma of France. There it is. Fuel got cheap. And GE was making excellent money selling a conventional engine that the GE36 would have made obsolete. So a machine that burned 30% less fuel got shelved because fuel wasn't expensive enough to care. But the blade knowledge did survive. This bolstered GE to use composite fan blades for the GE90 engine, which required a lightweight, durable material solution for the engine's large front fan. And some of the DNA goes back further still. Actually, though, some of the key technologies incorporated in the GE90 trace their roots to joint GE/NASA research in the 1970s. The 1970s. Government-funded research, decades before there was a product to sell. That's the timeline nobody accounts for when they price a jet engine. And this is the part where I want you to actually sit with the engineering, because it explains everything about why the GE90 looks the way it does. Why do you even want composite blades? Simple. Physics. To make a very quiet engine with very high thrust, you want a huge fan spinning relatively slowly. Slow fan tips mean less noise, but a huge fan needs huge blades, and huge blades made of titanium are heavy. Heavy blades mean a heavy fan disc to hold them, which means a heavier shaft, heavier bearings, heavier containment casing. Weight compounds. Suddenly, your efficient engine is a boat anchor. GE described the logic exactly this way. The front fan turns more slowly than the front fan of jet engines of similar thrust, and thus it is quieter. But the blades have to be huge to pull enough air into the engine to produce the super high thrust. Traditional titanium blades would have resulted in far too much engine weight. The solution: the GE90 blade's carbon fiber polymeric material and a titanium leading edge for extra protection were a lightweight and durable solution. Carbon fiber for the body, titanium along the front edge, where things hit it. That's the recipe. And the testing? Brutal. Typical titanium blades absorb energy and bulge when they hit obstacles such as a bird. But ordinary composites can delaminate and break. That's the exact failure mode that killed the RB211's composite blades in the 1960s. Composites don't dent, they shatter. So GE went and broke a lot of them on purpose. The team ran hundreds of intensive tests, simulating bird strikes, rain, snow, and hailstorms at GE's jet engine boot camp in Peebles and the Wright-Patterson Air Force Base, both in Ohio. GE conducted hundreds of intensive tests on the new composite material to determine its breaking points. That's Nick Cray, a GE composite design engineer who worked on the blade. It worked. Powering an early model of Boeing's 777 aircraft, the first GE90 engine certified in February 1995, and thus marked the first aviation use of the revolutionary composite fiber polymeric material on a jet engine's front fan blade. First in aviation history, on a fan blade, on a passenger jet. And they weren't just first, they stayed first. This line stopped me cold when I read it. The engineering is so difficult that to this day, GE is the only company with composite fan blades in service. That was written in 2015, 2 decades after certification. Nobody else had matched it. If you're enjoying this, drop a like. It genuinely helps the channel, and there's a lot more coming. Now, certification day itself has a great story attached to it. On the table were certification documents for a giant high-bypass turbofan aircraft engine called the GE90, which the company had spent the previous decade developing. Without certification, the engine couldn't fly on Boeing's 777 airplane. The FAA signed. And then, no celebration. We put the certificate straight on the fax machine and sent it to Seattle, remembers Philip Rambo, who was present in the room as a senior engineer on the GE90 program. A fax machine. That's how the biggest engine in the world got cleared to fly. Over in the Pacific Northwest, a team of technicians was standing by. They immediately printed an aircraft nameplate for a twin-engine Boeing 777 that was waiting on the runway. That plate gave the 777 the all-clear to fly. It made its first test flight with the GE90 engine that same afternoon. There's an aircraft sitting on a runway waiting for a piece of paper to come out of a fax machine. Entry into service came a few months later. The first General Electric-powered Boeing 777 was delivered to British Airways on November 12, 1995. The aircraft, with 2 GE90-77BS, entered service 5 days later. And it's worth noting where the engine actually started, thrust-wise, because the famous 115,000 pound number was a long way off. The GE90 was initially certified at 84,700 pounds thrust, but it is capable of thrust levels well beyond that, 84,700. That's the number GE90 number 1 was allowed to make. The growth came fast, though. The first growth model, the GE90, 92B achieved its rated thrust of 92,000 pounds in the spring of 1996. And behind closed doors, they were already pushing far past anything certified. Research engines have topped that. The GE90 has operated for more than 150 hours at thrust levels above 100,000 pounds and has demonstrated a thrust capability of 110,000 pounds. 150 hours above 100,000 pounds of thrust in 1996, years before anyone would buy an engine that powerful. GE knew what they had. The market just hadn't caught up yet. The engine is designed to power all models of the 777 in development or planned, plus other subsonic commercial widebodies contemplated for introduction over the next 20 years. $2 billion, a decade of development, a world first in materials, an engine that would eventually break world records. And it was, commercially, a disaster. Here's where the story turns, and it turns hard. Initial service was affected by gearbox bearing wear concerns, which caused the airline to temporarily withdraw its 777 fleet from transatlantic service in 1997. British Airways, The launch customer, the airline whose logo was on the very first GE90-powered 777, pulled its 777S off transatlantic routes. The single most visible customer, publicly grounding the aircraft over engine concerns. British Airways aircraft returned to full service later that year. Problems with GE90 development and testing caused delays in Federal Aviation Administration certification. British Airways soon replaced the GE90 with the Rolls-Royce Trent 800 on their 777S. They switched. The launch customer went to the competition, and the market's verdict was blunt. In addition, the GE90's increased thrust was not yet required by airlines, and it also was the heaviest engine of the three available choices, making it the least popular. Read that carefully, because it's savage. Too powerful for what airlines actually needed. Too heavy. Too expensive. Last place. GE tried to find other homes for it. Then CEO Brian H. Rowe went so far as to offer to pay for the development of the GE90 for the Airbus A330, but Airbus rebuffed the plan, instead choosing to focus on the four-engine A340 for the long-haul market. GE offered to pay Airbus to take the engine. Airbus said no, and in 1998, the wheels came off. The massive and futuristic GE90 engine, touted in the 1990s as the world's largest and most powerful jet engine, had become an embarrassing business failure by 1998. Troubles culminated in 1998 with GE Corporate taking a $275 million tax write-off after canceling a GE90 upgrade development program to make the engine capable of 102,000 pounds of thrust for a larger Boeing 777 model on the drawing board. $250 million written off. Program canceled. And that program was the one meant to unlock more thrust, the thing that would eventually become the engine's entire reason for existing. Jack Welch, then running all of General Electric, had a line about it that has aged into pure irony. The GE90 is the most money I've ever spent on a new product, so let's hope it all works out. At that point, it really didn't look like it was going to. So what happened? How does the biggest failure in the company's aviation history turn into the engine that defines an era? Two things. One is a person. The other is a hunch that turned out to be right. He became president of GE Aviation in 1997 after leading several GE operations. While he wasn't a propulsion engineer, he trusted his technical leaders in Evendale. That's Jim McNerney. 1997 was the magic year for GE when Jim McNerney entered the position of president of the company, spearheading one of the most significant turnaround strategies seen in the engine industry. And the hunch? The engineers noticed something in the data. For one, the GE90's fuel efficiency quietly attracted rave reviews from operators of the extended range 777-200ER, which entered service in 1997. The more the 777 grew, the better the GE90 performed against its competitors. That's the key. That's the whole thing. The GE90's problem was never that it was bad. It was that it was too big for the airplane that existed. It was an engine waiting for an aircraft to grow into it. And Boeing was about to grow the aircraft. And before we get to how Boeing changed the airplane, there's a piece of engineering that happened in 1998 that almost nobody outside the industry knows about. It's the quiet turning point. For the GE90 94B engine variant developed in 1998, GE designed a more capable compressor. It was the foundation for much bigger things to come. That's it. That's the sentence. A better compressor, on a variant most people have never heard of, in the exact year the program was being written off as a failure. And what went into it was a computational technique that was still relatively new at the time. Rated at 94,000 pounds of thrust, the GE90 94B builds on the proven success of the GE90 family, adding key performance-enhancing technologies such as the three-dimensional aerodynamic 3D Aero high-pressure compressor, a key component of the performance improvement to be incorporated into the GE90 115B engine currently under development. 3D Aero is a computer design and analysis program. Its use on the -115B engine design delivers improved fuel burn. So while the accountants were writing off $275 million, the engineers were quietly building the thing that would save the program. Think about what a compressor actually does for a second, because it's the least glamorous and most important part of the whole machine. Air comes in. Before you can burn fuel in it usefully, you have to squeeze it. Stage after stage of rotating blades and stationary vanes, each one raising the pressure a little more. By the time it reaches the combustor, it's been compressed enormously. The tighter you squeeze, the more energy you extract from every drop of fuel. That's thermodynamics. That's it. That's the whole game. The GE90's high-pressure compressor ran at a 23:1 ratio. And getting there without the airflow stalling, without the blades fluttering apart, without the whole thing surging. That's where the difficulty lives. 3D Aero meant you could model the shape of every blade in 3 dimensions and see, computationally, where the air was going wrong before you ever cut metal. In the mid-1990s, that was close to magic. The -94B was validated on a real airplane too. An Air France 777-200ER is being used as the test bed for the new engine. And the certification work was not casual. After a recent series of rigorous tests for FAA certification, GE90 94B engines have completed more than 1,400 hours of testing and received FAA flight test certification this month. 1,400 hours on the variant nobody talks about. Now, Boeing wanted longer, heavier, farther-flying 777S, the 300ER, the 200LR, the freighter. For these aircraft, a more powerful engine in the 100,000 lbf 440 kN thrust class was required, leading to talks between Boeing and engine manufacturers. Suddenly, the fat, expensive, overpowered engine was the only one in the room with headroom. GE went for it. In late 1998, GE aviation leaders traveled the globe to generate enthusiasm from several major carriers, most notably Air France, for a new GE90 being proposed to produce an unheard of 115,000 pounds of thrust for bigger, longer-range 777S being evaluated by Boeing. General Electric offered to develop the GE90 115B engine, while Rolls-Royce proposed developing the Trent 8104 engine. And GE played it aggressive. They didn't just want to be an option, they wanted to be the only option. While frustrated by the GE90, Welch agreed to support a larger GE90 if a sole-source engine deal on the 777 could be reached. 8 months of negotiations and lobbying with Boeing ensued. And then, in July 1999, in a dramatic decision, Boeing selected the GE90 115B turbofan in July 1999 as the exclusive power for longer-range Boeing 777-300ER and 777-200LR jetliners. It was the greatest comeback in modern GE aviation history. Under the deal with General Electric, Boeing agreed only to offer GE90 engines on new 777 versions, exclusive. No Rolls, no Pratt. If you wanted a 777-300ER, you were buying GE90S. Not a choice, a requirement. The tension in that room, in the days before it was announced, must have been unbearable. There's an exchange that captures it perfectly. 2 days before Boeing announced the deal, McNerney turns to Chadwell, his trusted lieutenant, and asked pointedly, "We didn't get snookered, did we?" With a broad smile and calm assurance, Chadwell, who had a history of selling big bets to his bosses, responded, "Jim, it's a good deal. It was a good deal. Comment below. Would you have kept funding that engine in 1998 or killed it?" Because plenty of very smart people wanted to kill it. Now let's talk about the machine itself, because the GE90 115B is genuinely absurd. Start with the fan. The 128-inch fan diameter on the latest GE90 115B for the Boeing 777-300ER, 777-200LR, and the 777 freighter. That's more than 10.5 feet across, the fan alone. 22 blades. The engine contains 22 fan blades, each of which is 4 feet long and weighs less than 50 pounds. And here's a detail that gets lost. Those blades aren't just moving air. Every GE90 115B engine contains 22 of these fan blades, which add approximately 2,000 pounds to the engine's thrust capability, while providing better fuel burn. The curve isn't styling, it's structural. The artistic, curved design serves a key function to enable the fan blades to withstand supersonic airwaves generated during flight. Supersonic airwaves on a subsonic airliner. Because the blade tips are moving fast enough, relative to the incoming air, to generate shock waves. The shape exists to survive that, and the guts of the engine were equally advanced for the time. The GE90's all-composite fan blades, the 23-to-1 high-pressure compressor, and dual annular combustor deliver the lowest fuel burn, lowest noise, and lowest total emissions on the 777. There's also a piece of the design almost nobody talks about, and it involves inventing a metal, Feeding 115,000 pounds of thrust through a shaft creates loads. And there's a worst-case scenario every engine has to survive by law: the fan blade-off event. A blade departs at full speed. The engine has to contain it, and the shaft has to survive the instantaneous, violent imbalance. The initial GE90 fan shaft design loads were greatly increased for operational torque and the fan blade-off condition. To accommodate the increase in fan shaft torsional and bending stresses, a steel alloy, GE1014, not previously used in aircraft engines, was required. They needed a steel that had never been used in an aircraft engine. So that's what went in. And the thrust. Let's do the thrust. The certified rating is 115,300 lbf, 513 kN. That's what it's allowed to make in service. But that's not what it can make. According to the Guinness Book of Records, at 127,900 lbf, 569 kN, the engine held the record for the highest thrust achieved by an aircraft engine. 127,900 pounds of thrust from one engine. And how did they get there? This is my favorite piece of the whole story. This thrust record was reached inadvertently as part of a 1-hour triple redline engine stress test using a GE90 115B development engine at GE's outdoor test complex near Peebles, Ohio. Inadvertently. They weren't chasing a record. They were torture testing the engine. Triple red line means maximum fan speed, maximum core speed, and maximum exhaust gas temperature, all at once, all held there. An hour of that. And in the middle of trying to hurt the thing, it accidentally set a world record. It also broke its own previous record doing it. It eclipsed the engine's previous Guinness World Record of 122,965 lbf 546.98 kN. The GE90 engine held the record as the world's most powerful jet engine for nearly 15 years, clocking in at 127,900 pounds of sustained thrust in 2002. 15 years. Unbeaten. But raw power was never the actual point. What the GE90 really changed was where twin-engine airplanes were allowed to fly. Here's the concept. ETOPS. Extended Range Twin-Engine Operations. It's a rule about how far a twinjet is permitted to be from the nearest suitable airport at any moment in its flight. Because if one engine quits, you have to get down somewhere on the remaining one. More reliable engines, more ETOPS minutes. More minutes, bigger circles on the map. Bigger circles, routes that were previously impossible. Together, efficiency, reliability, and power boosted the extended operations ETOPS of a Boeing 777-300ER to around 345 minutes, meaning that the airplane could, if needed, fly for nearly 6 hours on a single engine from the nearest airport where it could safely land. Nearly 6 hours on one engine. That's the permission slip. And Philip Rambo, the GE90 engineer from the fax machine story, put it in the plainest terms possible. That really opened up the southern hemisphere and stretched the legs of twin-engine operations. Now, the economics. This is the part passengers never see but pay for every time they buy a ticket. For Boeing, going from 4 engines used by planes like the iconic Boeing 747 to 2 was not a case of showing off. It allowed airlines with the 777-300ER in their fleet to cut expenses by lowering fuel bills. Fuel amounts to as much as 20% of an airline's operating costs, and also by lowering its maintenance bill since it's easier and faster to take care of 2 engines than 4. 2 engines to maintain instead of 4. Half the overhauls, half the spare engines sitting in a warehouse. This improved the economics for passengers as well as freight. That's the death of the 4-engine jumbo, right there, described in dry business language. Not a dramatic event, just arithmetic that stopped working in the 747's favor. The scale of the GE90's eventual success is hard to overstate. With more than 2,800 GE90 engines delivered around the world, GE Aerospace and its global network of maintenance, repair, and overhaul MRO providers are anywhere that our customers need support. And GE never stopped fiddling with it. GE Aerospace engineers have enhanced the GE90 115B engine's compressor, combustor, and high and low pressure turbine components to reduce weight, improve fuel efficiency, and enhance durability. The result: 3.6% reduction in fuel burn from initial launch specification. 3.5% doesn't sound like anything. On a fleet flying millions of hours, it's an enormous amount of fuel that simply never gets burned. There's also a piece of trivia here that I love because it's such a perfect footnote. The GE90 115B, the most famous variant, The record holder, the engine everybody pictures, was never certified on the original 777-300. The engine variant that was certified for use on the 777-300 was the GE90-92B instead, and the -300 had a choice of engines. In addition to the General Electric GE90-92B, the Boeing 777-300 is also certified to operate with Rolls-Royce Trent 892 and Pratt & Whitney PW4098 engines. The exclusivity only ever applied to the newer, longer-range models, and the Boeing 777-300 entered commercial service in 1998 with Cathay Pacific. Okay. Let's stay with the competition for a minute, because the other giants have stories worth telling, and one of them has a very bad chapter. The Pratt & Whitney PW4000 family is, on paper, one of the great commercial engine programs, spanning thrust ratings from 52,000 to 99,000 lbf across 3 distinct fan sizes. The PW4000 family is among the most versatile engine programs in commercial aviation history. It powered the Boeing 747, 767, and 777, as well as the Airbus A300 and A310, and the McDonnell Douglas MD-11. 3 fan sizes: PW4000, 94-94-inch fan; PW4000, 100-100-inch fan; PW4000, 112-112-inch fan. Same basic core, scaled up and up. The numbers on service life are genuinely impressive. In 30 years between June 1987 and 2017, more than 2,500 engines have been delivered, logging more than 135 million flight hours. The PW4000 has a dispatch reliability rate of 99.96% and is approved for ETOPS 180, 135 million flight hours. That's not a machine. That's an institution. And the PW4000 also owns one of the most extraordinary events in ETOPS history, March 2003. A United 777 Mid-Pacific. United Airlines Boeing 777, carrying 255 passengers, flew over the mid-Pacific Ocean against strong headwinds for 192 minutes. Under single-engine power March 17th to land without incident at Kona on the western coast of the Big Island of Hawaii. 192 minutes, over 3 hours, over the Pacific, on one engine, 255 people on board. Boeing confirmed that it was the longest single-engine diversion during extended twin operations ETOPS since the advent of transoceanic twin-engine flights 20 years ago, and it landed without incident. That is the entire ETOPS philosophy working exactly as designed. But the PW4000 112 also has a serious problem in its history, and it centers on the fan blades, which brings us right back to materials. Pratt's 112-inch fan used titanium. Specifically, the PW4000 112-inch engine fan blade is a hollow core, wide-cored airfoil made of a titanium alloy with 6% vanadium and 4% aluminum as alloying elements. The fan blade is about 40.5 inches long from the base of the blade root to the tip of the airfoil. Hollow core. That's how you keep a titanium blade that big from being unbearably heavy. You make it hollow. February 2018. A United 777 over the Pacific, heading for Honolulu. On the 13th of February 2018, United Airlines Boeing 777-222-N773UA suffered a fan blade off event and lost most of the inlet duct and both the left and right fan cowls of its No. 2 Pratt & Whitney PW4077 engine. The aircraft made a safe landing without injuries to the 374 persons on board. 3 years later, February 2021, Denver. Boeing 777-200's right hand PW4077-112 had a blade failure shortly after taking off from Denver, causing significant engine damage. 2 fan blades had broken off. One had suffered metal fatigue and possibly chipped another blade, which also broke off. If you've ever seen that footage, the engine cowling gone, the ring of the engine glowing, passengers filming it out the window. That's this event. And this is the sentence that made regulators move immediately. The failed blade was compliant with the inspection intervals set by the FAA following the 2018 incident. The blade broke while following the rules, which means the rules were wrong. The FAA grounded the affected 777S and issued an emergency airworthiness directive on the 23rd of February, requiring a thermal acoustic inspection TAI of the -112 fan blades before next flight. Japanese authorities and the UK's CAA followed suit, grounding 69 in-service and 59 in-storage Boeing 777S. This action affected approximately 130 aircraft operated by airlines including United, Japan, Airlines, and All Nippon Airways. The NTSB's finding was blunt. The report highlighted inadequate inspection methods and insufficient frequency of checks, which failed to identify low-level cracking in the blade's midspan region, marking this as the fourth such PW4000-112 fan blade separation incident investigated by the NTSB since 1991. The fourth, since 1991. I want to be careful here, because this is not a story about a bad engine. An engine with 135 million flight hours and 99.96% dispatch reliability is not a bad engine. It's a story about how failure modes hide inside things that work almost all the time, and how inspection is the only thing standing between almost always and always. And one more consequence. The PW4000-112's 2021 incident accelerated the transition of 777 operators to the newer and more advanced General Electric GE9X on the 777X, effectively marking the beginning of the PW4000's withdrawal from frontline service on the largest widebodies, now Rolls-Royce. Because the modern Rolls story is fascinating, and it is not the story of chasing GE on thrust. The Trent XWB powers the Airbus A350, and Rolls made a very deliberate choice with it. It keeps the characteristic three-shaft layout of the Trent, with a 3M120 in fan, an IP and HP spool. The XWB-84 generates up to 84,200 lbf, 375 kN of thrust, and the XWB-97 up to 97,000 lbf, 431 kN. The engine has a 9.61 bypass ratio and a 51 pressure ratio. It is the most powerful among all Trent engines. Notice the fan, a 118-inch diameter fan with 22 blades, smaller than the GE90's 128. Notice the thrust, 97,000 pounds maximum. Well, under the GE90, 115B's 115,300. Rolls wasn't trying to win the thrust war. They were building the efficiency engine for a smaller, lighter aircraft, and they're not shy about it. The Trent XWB is the world's most efficient large aero engine in service. Designed, engineered, and optimized for the A350, these perfect partners deliver 25% lower fuel burn and CO2 emissions. And the reliability record early on was remarkable. It took 2 years to reach 1 million flying hours and 9 months for the second million by July 2018, as 500 were delivered. At that time, it had a 99.9% dispatch reliability and had had no in-flight shutdown. 2 million flight hours before a single in-flight shutdown. It had its first in-flight shutdown on the 11th of September 2018, as the fleet accumulated 2.2 million flight hours. There's also a design detail here that is one of my favorite pieces of engineering trivia in all of aviation. The engine features a rubber-tipped spinner, a patented design innovation developed by a graduate to mitigate ice accumulation at high altitudes. The natural vibration of the flexible rubber prevents ice crystals from forming on the cone, where ice first forms, ensuring they are shed before they can enter the engine intake and cause potential damage. A graduate engineer's idea. Rubber on the nose cone. It vibrates as the engine spins, and ice can't grip it. Simple, cheap, patented, and it solves a problem that could otherwise send ice crystals straight into the engine core. But the Trent XWB has its own pressure point, and it's the high-thrust variant. To get from 84,000 to 97,000 pounds, Rolls had a choice: build a bigger engine or push the one they had. They pushed. The engine produces 97,000 pounds of thrust, and to achieve this, the Trent XWB-97 has a 5% larger core while the fan runs 6% faster. It uses thicker titanium fan blades to better handle the added stress, while the fan casing has also been strengthened. Same fan diameter. Approximately 15% more power compared to the baseline model while maintaining the same 118-inch 3M fan diameter. And the trade-off is heat. Rolls-Royce was able to maintain the same bypass ratio for the Trent XWB-97 as its less powerful sibling, but the engine gains its extra power in part by pushing more air through the larger engine core, which burns significantly more fuel. This is compensated for by increasing the engine's internal temperature, but this also strains the engine more. Rolls-Royce's own QO for civil large engines said the quiet part out loud. The Trent XWB-97 will be the highest thrust engine we have ever certified, the highest operating temperatures, and the most advanced cooling systems we have ever designed in a civil engine. Highest temperatures they've ever designed. And in aviation, heat is the enemy of time on wing, which is why this happened publicly at the Dubai Air Show. At the 2023 Dubai Air Show, the president of the Emirates, Tim Clark, said the A350-1000's engine, Trent XWB-97, would offer only a quarter of the time between maintenance visits compared to their needs. A quarter. Meaning, it would need to come off the wing 4 times as often as Emirates wanted. Now, Tim Clark is famously blunt and famously good at negotiating in public. Citigroup analysts claim these comments form part of the airline's commercial negotiation tactics involving prices or guarantees. But the physics behind the complaint is real. They claim the higher thrust 97 XWB would be expected to run at higher temperatures with faster wear, particularly in hot and sandy climates, noting Qatar Airways operates the Trent XWB-97 without major issues. Hot air is thin air. Thin air means the engine works harder for the same thrust. Sand is an abrasive that eats turbine coatings. Dubai is hot and sandy. That's not a marketing dispute. That's an operating environment. Rolls-Royce was later reported to be working with Emirates to improve durability in hot and sandy conditions. If this is your kind of content, subscribe. I go deep on this stuff regularly. So, GE90 wins the thrust crown, holds it 15 years, and then loses it. To whom? To itself. Derived from the General Electric GE90 with a larger fan, advanced materials like ceramic matrix composites, CMCs, and higher bypass and compression ratios, it was designed to improve fuel efficiency by 10% compared to the GE90. The GE9X, built exclusively for the Boeing 777X, and it is the biggest thing GE has ever built. The GE9X engine is in the 100,000-pound thrust class and has the largest front fan at 134 inches in diameter, with a composite fan case and 16 fourth-generation carbon fiber composite fan blades. 134 inches. And this comparison never gets old. The engine's fan measures 134 inches in diameter, wider than the fuselage of a Boeing 737, making it the largest turbofan ever produced. The fan of one engine is wider than the entire body of a 737, passengers and all. But the number that actually tells you how far the technology has come isn't the diameter, it's the blade count. The GE9X has 16 blades, whereas the similarly sized GE90 has 22, and the smaller Jax has 18. Bigger fan, fewer blades. Think about what that means. Each individual blade is doing dramatically more work. And the reason you want fewer of them. Having fewer fan blades reduces the engine weight, improves aerodynamic efficiency, and allows the low-pressure LP fan and booster to spin faster to better match its speed with the LP turbine. Nick Cray, the composite blade engineer, explained the new blade design. They will use stiffer carbon fibers so GE can make them longer and thinner. But the trailing edge changed material entirely, and the reasoning is beautiful. Carbon fiber is very stiff and not that flexible, so that when a bird or something else hits the blade, it creates a shockwave deep inside it. But the glass composite can deform better and deflect stress on the blade, so the blade is a hybrid. The fan blades feature steel leading edges and glass fiber trailing edges to better absorb bird impacts with more flexibility than carbon fiber. Steel at the front for impact, carbon fiber for stiffness, glass fiber at the back for flex. 3 materials, 1 blade, each doing the job it's best at. Deeper in the engine, the real revolution isn't composites at all. It's ceramics. Lightweight and durable ceramic matrix composite CMC material in the combustor and turbine. Why ceramics? Ceramic matrix composites in the turbine section replace traditional metal alloys in some of the hottest zones, allowing higher operating temperatures with less cooling air. Follow that logic, because it's the core of modern engine efficiency. Hotter core, more efficient. But metal melts, so you bleed cool air off the compressor and pipe it through the turbine blades to keep them alive. That bleed air is air you're not using for thrust. It's a tax. Ceramics take the heat. so you pay less tax, so you get more efficiency out of the same fuel. The rest of the GE9X spec sheet is just relentless. A highly efficient 27:1 pressure ratio high-pressure compressor. A third-generation low-emissions TAPS 3 combustor. Its 61:1 overall pressure ratio. The bypass ratio is planned for 10:1. Bypass ratio of 10:1 means, for every unit of air that goes through the burning core, 10 go around it. Almost all your thrust is just the fan moving cold air backwards. The core exists mostly to spin the fan, and that air volume is staggering. Operating at a high bypass ratio of 10:1, the GE9X can process and propel up to 3,850 pounds of air every second when operating at maximum thrust, nearly 2 tons of air per second, per engine. The engine physically dwarfs everything. Its nacelle is 184 in 4,700 mm wide. Each engine weighs approximately 21,000 pounds, and it was so large it created a testing problem. As it was larger than the GE90, the GE9X could only be installed under the wing on the Boeing 747-400 with its larger main gear struts and bigger tires, and not the previous 747-100 GE testbed. They had to upgrade the flying testbed. The engine outgrew the airplane that carried it. And in November 2017, at Peebles, Ohio, same test site, same triple red line ritual, the record fell. On November 10, 2017, a GE9X engine reached a record thrust of 134,300 lbf, 597 kN in Peebles, a new Guinness World Record breaking the GE90 115B 127,900 lbf, 569 kN record set in 2002. The block test engine ran at its operational limits at triple redline conditions, maximum fan speed, maximum core speed, and maximum exhaust gas temperature. And GE's CEO of aviation at the time, David Joyce, said something that echoes the GE90's accidental record perfectly. While we didn't set out to break the thrust Guinness World Records title, we are proud of the engine's performance. Twice now. 2 engines, 2 world records, neither one on purpose. They were just trying to break their own machines. Here's the twist that surprises most people, though. The GE9X is the most powerful engine ever tested, but in service, it's rated at 110,000 lbf, 490 kN, which is less than the GE90 115B's 115,300. The newer, bigger, record-setting engine is certified for less thrust than its predecessor. Why? Because the airplane got better. This apparent reduction in power requirements stems from the 777X's highly efficient aerodynamic design. The aircraft features expansive wings that cover 5,025 square feet, generating exceptional lift characteristics. According to GE9X program manager Ted Engling, Boeing's engineering team accomplished remarkable efficiency improvements in the aircraft's lift-to-drag ratio, reducing the thrust requirements despite the aircraft's larger size. Better wing, less thrust needed. The engine doesn't have to work as hard, and the operational headroom that creates is enormous. It's been tested to produce up to 134,000 pounds of thrust during testing, but will only be rated for 110,000 pounds of thrust in commercial service, meaning that the engine will never be operating at close to its true capabilities. That's a machine living permanently below its limits. In engineering terms, that's a very, very good place for a machine to be, especially compared to the Trent XWB-97, which is being pushed hard to hit its number. The certification effort was on another level too. The GE9X has been through the most rigorous testing program of any GE Aerospace commercial aircraft engine in history. The engine has now passed through more than 31,000 total engine cycles of testing, including over 9,000 endurance cycles and 2,300 dust ingestion cycles. Dust ingestion cycles. They fed it sand, deliberately, thousands of times, precisely the environment that's causing headaches elsewhere. The GE9X engine achieved FAA type certification on September 25, 2020, after 8 test engines accumulated just under 5,000 hours and 8,000 cycles of rigorous ground and flight testing. This milestone followed over 400 hours of dedicated flight testing on GE Aerospace's Boeing 747-400 flying testbed. GE Aerospace invested more than $2 billion in the development of the program. $2 billion. Again, the same terrifying number as the GE90. But this time, GE knew exactly what it was buying. And notice one thing about the 777X that makes the whole competitive landscape click into place. There is no engine choice. The GE9X is the only option. not because of a sales deal. The GE9X became the sole engine choice, not because of commercial exclusivity deals, but because the performance envelope required categorically exceeded what competitive offerings could provide. No other engine in service or development could match the specific combination of thrust-to-weight ratio, fan size, and fuel burn that the 777X's design demanded. And could a competitor build one? Technically, yes. But the timeline and investment required would be enormous. GE Aerospace spent the better part of 3 decades building the composite fan technology, CMC materials capability, high-pressure compressor design tools, and manufacturing infrastructure that the GE9X relies upon. 3 decades. That's the moat. And it starts in a NASA-funded lab in 1984, building an experimental engine that never went into production. Every one of those wasted years bought something. So let's come back to where we started. That blade on the wall in New York. The Museum of Modern Art in New York City has acquired the world's largest jet engine fan blade, produced by General Electric company GE, into its architecture and design collection, November 2004. MoMA's own description of it is the most eloquent thing anyone has written about a jet engine part. The GE90-115B fan blade is a powerful fusion of cutting-edge engineering and design, and its astonishingly beautiful undulating form is a pure expression of its aerodynamic function. A pure expression of its aerodynamic function, meaning nobody made it pretty. It's pretty because of what it has to do, and the museum connected it to something much older. Its inclusion in MoMA's collection continues a tradition started in 1934 with the exhibition Machine Art, in which advanced airplane propellers were shown together with coils, ball bearings, and other machine parts of equally honest beauty. Honest beauty, 1934. Propellers next to ball bearings. There's a second one, too, closer to home. There is also a GE90-115B blade on display at the Museum of Modern Art MoMA in New York City, and one was donated to the Cincinnati Art Museum, minutes from GE's Evendale plant where the thing was designed. And Nick Cray, the engineer whose work hangs on that wall, gets the line that sums up his own career better than any museum caption. Nick Cray is no Picasso, yet his work is on display at New York's Museum of Modern Art. His reaction to seeing his blade in an art museum? We are now working on the 4th generation of that technology. He's not looking at the wall. He's already 3 designs past it. So, what did all of this actually change? Look up. Right now, somewhere over the Pacific, there's a twin-engine airliner 5 hours from the nearest runway. Nobody on board is thinking about it. The cabin crew are doing a drink service. Someone's watching a movie. Someone's asleep with their head against the window. That's the achievement. Not 127,900 pounds of thrust. Not 134 inches of fan. Not a $2 billion development budget or a Guinness World Record set by accident while trying to destroy something. The achievement is that flying 6 hours from land on 2 engines has become so unremarkable that nobody notices it's happening. Rolls-Royce nearly died, proving that composite blades were too hard in 1971. GE spent 30 years proving they weren't. Pratt built an engine that flew 135 million hours and still had a fatal flaw hiding inside its inspection schedule. And the record for the most powerful jet engine ever built has now been set twice by the same company. Both times by accident. Both times while engineers were deliberately trying to break their own creation. Every one of those stories is really the same story. Someone decided the current limit wasn't actually a limit, and then spent an enormous amount of money and time finding out whether they were right. Sometimes they weren't. That's what receivership is. But when they were, when the bet landed, the result is a piece of black carbon fiber hanging on a wall in an art museum, 4 feet long, shaped by nothing but the demands of moving air. And the strange thing is, the people who made it don't visit it. They're too busy on the next one. If you made it this far, you're my kind of aviation nerd. Like, subscribe and tell me in the comments, which of these engines would you most want to see run at full power in person? I'd take the triple red line test at Peebles. An hour of an engine screaming at every limit it has, and nobody in the control room quite sure whether it'll survive. It did. Twice.